In this video, we are going to discuss part 3 of chapter 7, which is Solubility Equilibrium. At the end of this lesson, students should be able to define solubility, molar solubility, and the solubility product. Calculate the Ksp from the concentrations of ions and vice versa. Predict the possibility of the precipitation of slightly soluble ionic compounds. Define and explain the common ion effect, and perform calculations related to the common ion effect. Now, let's define the solubility. Solubility can be defined as the mass of solute that dissolve in a given quantity of solvent to form a saturated solution. The solubility equilibrium exists between the undissolved solid solute and the aqueous ion form. For example, the soluble salt of argentum chloride. Argentum chloride dissociates to form argentum plus ion and chloride ion. The salt is an ionic compound that is lightly soluble in water. They have their own solubility product, or Ksp. What is molar solubility? Molar solubility can be defined as the number of mole of solute in 1 liter of a saturated solution. Let's consider an example to determine the molar solubility of a soluble salt. The question is, at 25 degrees Celsius, the solubility of silver chloride is 0.00193 gram per dm cube. Calculate the molar solubility of silver chloride in water. Now, let's check the answer. First, calculate the relative molecular mass of the salt. The argentum chloride has a relative molecular mass with 143.5 gram per mole. When the solubility of the salt is divided by its relative molecular mass, it will obtain a molar solubility with 1.34 exponent negative 5 mole per dm cube. Now, what is the meaning of the solubility product? Solubility product can be defined as the product of the molar concentrations of the ion involved in the equilibrium, each raised to the power of its stoichiometric coefficient in the equilibrium equation. In a saturated solution of a slightly soluble ionic compound, an equilibrium exists between the undissolved solid salt and its dissolved ions. For example, argentum chloride, magnesium fluoride, argentum carbonate, and the calcium phosphate. Observe how the Ksp expression is written for each of the equation. You also can try these questions to improve your understanding. Now, let's discuss on how to perform calculations that involve Ksp. Example 1. The solubility of plumbum iodide is 1.2 exponent negative 3 mole per dm cube. Calculate its solubility product. To answer this question, first, let's assume that solubility is equals to X. Writing the solubility equilibrium expression, plumbum iodide is dissolved to form plumbum 2 plus ion and iodide ion. Since the solubility has assumed as X, thus 1 mole of plumbum 2 plus is equals to 1x. 2 mole of iodide ion is equals to 2x. By writing the Ksp expressions, that is equals to concentration of plumbum 2 plus ions times concentration of iodide ion to the power of 2, by substituting the value, it will obtain Ksp equals to 6.91 exponent negative 9. Now, let's take a look for example number 2. The solubility product, or Ksp, of calcium carbonate at 25 degrees Celsius is given 2.8 exponent negative 9. Calculate the solubility of calcium carbonate in gram per dm cube at this temperature. To answer these questions, first, let's assume that solubility is equals to X. Writing the solubility equilibrium expression, calcium carbonate solid will dissolve to form calcium 2 plus ions and carbonate ions. Since the solubility has assumed as X, thus 1 mole of calcium 2 plus is equals to 1X. 1 mole of carbonate ions is equals to 1X. Writing the KSP expressions, that is, concentration of calcium 2 plus times concentration of carbonate ions, by substituting the value, it will obtain the value of X that is equals to 5.29 exponent negative 5. The X value obtained from the calculations will give the molar solubility value with 5.29 exponent negative 5 mole per dm cube. By calculating the molar mass of the calcium carbonate, it will obtain 100 gram per mole. To determine the solubility in gram per dm cube, the molar solubility is multiplied with its molar mass. Thus, it will obtain 5.29 exponent negative 3 gram per dm cube. You can try to answer more exercises to improve your understanding. Now, let's discuss on how to predict the precipitation for the soluble salt solution. Precipitation reaction occur when cations and anions in aqueous solution combine to form an insoluble ionic solid that is called a precipitate. A mixture of two solutions will produce a precipitation or not depending on the ion product Q present. The general equation of solubility equilibrium for a slightly soluble salt of Ma can be written as shown in the equation. Ma salt dissociate to form M plus aqueous ion and A minus aqueous ion. The solubility product or KSP expression can be written as KSP equals to concentration of M plus ion times concentration of A minus ions. The ion product or Q of a salt is the product of the ions in the solution raised to the same powers as in the solubility product or KSP expression. For a reaction that involves a soluble salt of Ma solid, dissociate to form M plus aqueous ion and A minus aqueous ion. The ion product or Q expression can be written as Q equals to concentration of M plus ions times concentration of A minus ions. The Q has the same form as KSP, but the concentrations of the ion are not equilibrium concentrations. By comparing Q and K, three possible conditions for an aqueous solution of an ionic solid. First, when Q equals to K, that means the system is in equilibrium. Second, when Q less than K, that means the system is not in equilibrium. And finally, when Q greater than K, that also means the system is not in equilibrium. Based on the equation of dissociation of soluble salt of Ma that dissociate to form N plus aqueous ion and A minus ions, when the value of Q is equals to KSP, that means the solution is a saturated solution. The undissolved salt or solid and its dissolved ions exist in equilibrium. When Q less than KSP, that means the solution is unsaturated. More ionic solid or salt will dissolve to increase the ion's concentrations until the Q reach equals to KSP. The equilibrium position will shift to the right, thus no precipitation of Ma soluble salt. By considering the same reaction, when Q greater than KSP, That shows the solution is supersaturated. The ionic solid will precipitate. That means the equilibrium position shifts to the left. Therefore, precipitation of Ma will obtain. Now, let's discuss an example to determine the precipitation. The question is, if 500 ml of 0.014 molar of calcium chloride is added to 250 ml of 0.25 molar of sodium sulfate, will a calcium sulfate precipitate form? Ksp is given with 2.0 exponent -4. To answer these questions, first let's determine the number of mole for each of the ions involved. The moles of calcium 2 plus ions is equals to 0.007 mole. The number of mole of sulfate ions is equals to 0.0625 moles. Convert the number of moles into concentrations by dividing with its total volume of the solutions. Thus, it will obtain the concentration of sulfate ions that is equals to 0.0093 molar and calcium 2 plus ions with 0.083 molar. Solubility equilibrium for calcium sulfate can be written as shown in the equation, whereas the calcium sulfate soluble salt dissociate to form calcium 2 plus aqueous ion and sulfate aqueous ion. The value of Ksp is given with 2.0 exponent -14. By substituting the value of the concentration obtained from the calculations, we can determine the ion product or Q. That obtained with 7.72 exponent -4. By comparing the Q and K, we can observe that the Q is greater than Ksp. Thus, the solution is supersaturated, so some of the calcium sulfate will precipitate. You can try to answer these exercise questions to improve your understanding. Now, let's discuss the common ion effect. Common ion is an ion that is common to two or more components in a mixture of solutions of ions. Common ion effect is the reduction in the solubility of salt in the presence of a common ion. Let's consider an example of slightly soluble salt of argentum chloride. The solubility equilibrium can be written as argentum chloride solid dissociate to form argentum plus aqueous ion and the chloride aqueous ion. When the NaCl is added to the saturated argentum chloride solution, the concentration of the chloride ions is increased. The chloride ions is the common ion. According to the Le Chatelier principle, the increase in the concentration of the chloride will cause the position of the equilibrium shift to the left, thereby causing some of the argentum chloride to precipitate. So, the solubility of argentum chloride will decrease until the Q that equals to Ksp. As a conclusion, the addition of common ions will reduce the solubility of a slightly soluble salt in its saturated solution. Now, let's consider another example on how to determine the solubility for a slightly soluble salt with the presence of common ions. The question is, if the solubility product Ksp for argentum chloride is 1.7 exponent -10, calculate the molar solubility of argentum chloride in water and in a solution of 0.1 molar of potassium chloride. Question 1. Molar solubility of argentum chloride in water. To answer these questions, let X be the molar solubility of argentum chloride in water. Writing the solubility equilibrium expression, argentum chloride slightly soluble salt dissociate to form argentum plus aqueous ion and the chloride aqueous ions. Since the solubility has assumed as X, thus 1 mole of argentum plus ions is equals to 1X, 1 mole of chloride ion is equals to 1x. Writing the KSP expression for the reaction, that will obtain the value of x is equals to 1.30 exponent negative 5. Thus, the solubility of argentum chloride in water is equals to 1.30 exponent negative 5 molar. Question number 2. What is the molar solubility of argentum chloride in 0.1 molar of potassium chloride? Let's assume Y, the molar solubility of argentum chloride in 0.1 molar of potassium chloride. Writing the solubility equilibrium expression of argentum chloride soluble salt is dissociated to form argentum plus aqueous ion and the chloride aqueous ions. Since the Y has been assumed as molar solubility of argentum chloride, so 1 mole of argentum plus ions is equals to 1Y, while the chloride ion is equals to Y plus 0.1. This is because the chloride ion has the presence of a common ion from the argentum chloride and potassium chloride, whereas we have assumed that solubility of argentum chloride that equals to Y and the KCl presence is 0.1 molar. Thus, writing the KSP expression, substituting all the values that give 1.7 exponent negative 10 of KSP equals to Y times Y plus 0.1. We can assume that value of Y is very small. This is due to the value of K that is very small than exponent negative 5. So, for Y plus 0.1, we can assume as 0.1 only. From the KSP expression, that is argentum plus concentration times chloride ion concentration, substituting the values, we obtain the value of Y that is equals to 1.7 exponent negative 9 molar. Thus, the solubility of argentum chloride in 0.1 molar of potassium chloride is 1.7 exponent negative 9 molar. Now, you can try more exercises to improve your understanding. That's the end of our lessons today. Bye!